Hello students, welcome to section 12.6, Spheres. The following is a list of definitions related to the study of spheres. You very likely know what a sphere looks like, but here's the definition. The set of all points that are a given distance from a given point called the center. Radius, as you again know, a segment whose endpoints are the center of the sphere though, and a point on the sphere. So instead of a circle, obviously, we're extending the radius to a sphere. A chord is a segment whose endpoints are points on the sphere. Diameter, a chord that contains the sphere's center. Tangent, a line that intersects the sphere in exactly one point. Hemispheres are two congruent halves of a sphere separated by a great circle. So as far as some of these terms are concerned, certainly a radius would make sense in the context of, and I'll go ahead and create a sphere for you, or maybe do my best to use the tools at my disposal and make them look three-dimensional here. So here's one circle, and typically when we see a sphere in 3 dimensions, we'll draw a second circle. What I'll do my best here to do is kind of give it a more three-dimensional-ish type of look. Okay. So as far as our object is concerned, again, this is as close to three-dimensional as I can probably get, although typically when we draw a sphere in 3 dimensions, we also draw this part of the circle here with dashed lines or dashed arc kind of measurements or depictions. So that's as good as I'm going to be able to probably do with the tools that I have. What I'd like to, though, do is include here all the aspects that are of relevance. Particularly, we've got our radius. So I'll create my radius here as such. Now the radius does in fact extend not just from the center to the point that I'm highlighting, but it extends to any point you can imagine on the circle. So there's a radius. There's another radius that goes in this direction, pretty much in all directions you can imagine. A diameter, or let's actually jump to chord. A chord is a segment whose endpoints are on the sphere. So a chord would look something like this. We've talked about chords before. Of course, a chord doesn't necessarily have to go through the center. If it does go through the center, that's fine. That is just a special type of chord. That would be a diameter, of course, which is the next term here, a chord that contains the sphere's center. So if I did draw another chord, but let's say going through the center, like so, it would look something like this, for example. Okay. A tangent line, as you already know, in this particular case, well, as you know, I should say, a tangent line touches one of our polygons or circles or anything for that matter in geometry, touches it at one point. So a tangent line in this particular context as well will also touch at one point and take shape like so. That is just fine. Okay, so there's our tangent. So we got a radius, a chord, a diameter, which is also a chord technically by definition, and we've got a tangent line. And then last but not least, hemispheres, again, two congruent halves. So simply the top half of your sphere is called a hemisphere, while the bottom half, again, is also called a hemisphere. Describe each object as either a model of a circle, sphere, or neither. Number one, a tennis ball can is technically a cylinder. If you can imagine a tennis ball can where obviously you put all the spheres inside of it, well, that's neither a circle nor sphere. A pancake, that's a circle, I would argue, if you make it into that particular shape, and if you're good at it, it'll look hopefully enough like a circle. Close enough, we'll say. Number three, the sun. I would argue that's a sphere as well. Any kind of ball is easy enough to identify as such. A basketball rim is a circle. The globe or a globe is a sphere. And then lastly, a lipstick container, we would say neither. I guess when it's in a closed position, we'd say it's a cylinder. Determine whether each statement is true or false. All lines intersecting a sphere are tangent to the sphere. Well, that's false. Now, in our depiction up above, yes, we do see a sphere of which a tangent here does in fact obviously touch the circle. Now, obviously, that's by definition a tangent, but if you had another line that cut through the sphere, intersecting it, that would technically go through, as we've seen with secants in the past, and that touches or technically intersects. Or same idea you can imagine here. Intersecting is the same deal, whether it's a sphere or even a circle, like we've seen in the past. But yeah, that would be 2 points. It's not a tangent in that regard, so that's false. Not all lines intersecting a sphere are tangent. They could be secant. Number 8, the eastern hemisphere of Earth is congruent to the western hemisphere. I would say absolutely. If in fact we're dividing it equally, and if in fact, when we depicted this many years ago and tried to decipher between the east and the west hemispheres, we did in fact do so such that it is a congruent hemisphere. On the next page, I do have a problem that I wanted to go through, a couple problems that I wanted to go through, numbers 1 and 3. Spheres can be defined as we've seen on the prior page, but more specifically using surface area. As you see with this formula, surface area S equals 4 pi r squared, and volume 4/3 pi r cubed. So for number 1, we have a radius of 9. The surface area of this particular sphere is 4 pi times 9 squared, and that roughly ends up being 1017.88 meters squared. The volume of the sphere, 4/3 pi times 9 cubed, which ends up being roughly 3053.63 meters cubed. Number 3, same idea. Be careful. The diameter of 40 is not what we're going to use specifically in context. We'll use the radius, right, of 20. 40 divided by 2, 20 as your radius. So 4 pi times 20 squared, that ends up being 5,026.55 feet squared. And then for volume, 4/3 pi times 20 cubed, and that ends up being 33,510.32 feet cubed.